Welcome to this FP3 derivation video for the surface area of a shape of revolution. First of all, this is the shape we're going to use. This thing here called a frustum, which is simply a cone with a smaller cone chopped off the top. This is the shape we're going to be using for our derivation. So let me make clear a few variables that I'm going to be using. First of all, this slant height I'm going to call S. And because we're going to have two of them, I'm going to call this one S1. Here, of course, you know, is the radius of the base. Call that R1. Over here, then, the smaller cone is going to have a slant height of S2 and a radius of R2, which, of course, is also the radius of the top section of the frustum. The slant height of the frustum, which is obviously S1 minus S2, I'm going to call delta S for reasons that will become clear soon. And of course, the radius of the bottom section of the frustum is still R1. And this is important because the surface area of a cone is equal to pi times the radius times the slant height. And of course the surface area of the frustum is going to be the surface area of the large cone minus the surface area of the small cone. So this is the basic idea we're going to use in terms of the shape. Now applying that to a graph, turn it on its side, very quickly put in some axes here. Let's say this is the y-axis, and here we have our x-axis. So in terms of the graph, the radius R1 is really going to be a y1, because that's going to be the y-coordinate of the function at a given point. And R2, similarly, y2. And here, this perhaps explains why I've used S instead of the more common L for the slant height of the cone, because this delta S for the frustum is going to be the small section of arc or chord of our function that we've looked at in the previous video for section 7. And we'll use that in our derivation later. So how it connects with an actual function, here you can see in red our y equals f of x function. The small section here is what we've just talked about, delta S, the small arc length that we've done before. Y, you can see this little bit here then is delta x, which we're not really going to use in our derivation, except that that's the thing that will tend towards 0 in order to make this limit an integral. So we will use that at the very end just to turn all of our deltas into d's so that we can integrate. And what we're actually doing, of course, is finding the surface area. That means this bit here, as you rotate this arc around. In pure 4, you will have done, or you will do, the volume of revolution, where you'll find the volume of the shape that is created by rotating this arc around here. But in FP3, we're looking at just the surface area, which is why this is a hollow shape being shown in the diagram. And the derivation is very similar if you rotate around the x-axis, or if you rotate around the y-axis, or if you use parametric equations. Basically, it just depends on what form you substitute for delta S based on our work that we did in the previous section for arc length. You know that we've got three forms around the x-axis, around the y-axis, and the parametric form. So depending on which one you substitute in at the end, gives you the different forms of this formula as well. So here are all of the background ideas. What follows then is a lot of algebra to show that from here you do get the formula that we have in the formula booklet. Starting us off, in order to connect things that we know to things that we don't know, so that we can get rid of the things that we don't know, we need to look at this triangle here and compare it to this smaller triangle here. So the larger triangle, based on what I've said about the variables we're using, has S1 here and Y1 here. The smaller triangle has S2 here and Y2 here. And of course these are similar triangles. These are similar triangles because the angles here are both the same angle off the large cone. They both have a right angle. So S1, Y1, S2, Y2 forms a similar triangle such that S1 over S2 must be the same ratio as Y1 over Y2. But we've also said that S2 is just S1 minus delta S. So I'm going to replace S2 with S1 minus delta S, where delta S is still this section here. This is S2, and this is S1. And that lets me write Y1 over Y2 is equal to S1 over S1 minus delta S. Because obviously we won't know what S2 is, it's not part of our shape, the frustum, and we don't even know what S1 is. That won't be part of our shape, the frustum either, so I need to get rid of S1, which is why I'm going to rearrange this in order to get S1 as the subject in terms of Y1, Y2 and delta S. So let's do that. Cross multiplying, get rid of the denominators, expand out that bracket, rearrange and factorize for S1. Gives us S1 is equal to Y1 delta S divided by Y1 minus Y2. And this is what we're going to use so that we've got just the y's, which we will know, they will be our function, and the delta S, which we can substitute for our arc length formula later. Why are we doing all of this? Well, we need the surface area of this section here. So we need the surface area of the frustum, which is the surface area of cone 1 minus the surface area of cone 2. So our surface area, mentioned on the previous slide, for a cone is pi times r times the slant height for a cone. So the surface area for the frustum, in this case with all of the letters that I've used, is pi times y1 times s1, which is the surface area of cone 1, minus the smaller cone, pi times y2 times s2, which we've already replaced with s1 minus delta s. Like so. So doing this part here allows me to substitute in here and here to get rid of the S1s and just have Y1, Y2 and delta S. So that's up there in the corner from the previous slide. Now substituting all of that in, pi Y1 times Y1 over Y1 minus Y2 minus pi Y2 times S1, which is Y1 delta S, I forgot the delta S here, over Y1 minus Y2, and expanding this bracket out, that was the first term here, we also need the second term here, that will be a plus pi Y2 delta S. And to add all of these fractions together, you know that I need the denominators to be the same. So let's put a y1 minus y2 there, and to make that true, we need it on the top as well. Expanding that out, I get pi y1 squared delta s minus pi y2 y1 delta s plus the first term here, pi y2 y1 delta s, and the second term minus pi y2 squared delta s. And if I've got all the denominators the same, that's one big fraction. Now the two terms in the middle here, minus pi y2 y1 delta s plus pi y2 y1 delta s cancel. And we can simplify this quite a lot by also now pulling out pi delta s as a common term between these two and factorizing what we've got left. So that gives us pi delta s y1 squared minus y2 squared divided by y1 minus y2. And the brackets here is the difference of two squares, so I can factorize that further into y1 plus y2 times y1 minus y2. And because that is still divided by y1 minus y2, we can now also cancel this to give us a final pi delta s y1 plus y2 for the surface area of the frustum. And what we've used is a tiny piece delta s, a very, very tiny piece of the arc. So the surface area here, we should really be calling it delta capital S, because it's just a very, very small section of the surface area of the whole shape. But that's good, because now we've got delta S capital on the left and delta S small on the right. Let me write that out one more time. Is equal to pi y1 plus y2 delta small s. But from previous work we know that delta s is equal to the square root of 1 plus delta y by delta x squared times delta x. And I'm not going to prove that, we know that from our previous section. I'm going to put this in. It's very annoying. And again, so delta S, capital, the surface area, is equal to pi y1 plus y2, substituting in what we know from before for little delta s, square root of 1 plus delta y over delta x, all squared, and the square root of that, delta x. So we're very close to the end now. This is the point where we can say, as delta x tends to 0, and we take it the limit so that we can integrate, we end up turning all of these deltas into d's. So you get d capital S is equal to pi, I'll come back to the y's in a second, 1 plus dy by dx squared, square rooted, integrated with respect to dx. Now the y's, as delta x tends to 0, y1 tends to y2, and they become effectively the same value. So I'm just going to call that y, which of course means that we end up with y plus y, which is 2y. Which is why our 2y comes in here. Now of course we can integrate both sides, and on the right we can't actually do the integral yet because we have not given a specific function, but we can pull the 2 and the pi outside because they're just constants. Y square root of 1 plus dy by dx squared with respect to x, and on the left d capital S becomes surface area. So this is our final formula. And I said earlier that you can get the different forms just by substituting in the different forms of delta S here, this was equal to delta S, little s. But we had different forms of that, and you could do it with respect to the y-axis rather than the x-axis, or parametrically instead of with y as a function of x. And if you substitute in the three different forms, you get your three different forms of the final answer here in just the same way.